Let's talk about sensors. The hidden champs in the modern world. The podcast series from Dr. Block. Brought to you by All About Sensors. Season 1, Episode 2. Dr. Block explains magnetometers, TMR technology for advancing magnetic sensor performance.
Welcome to a deep dive into the really fascinating world of magnetic sensors.
It's a hot topic right now.
Definitely. Today, we're sort of dissecting a pretty pivotal shift in this market. We're exploring why the traditional technologies are maybe reaching their limits.
Yeah, they're running out of steam for some applications.
And what's emerging as a truly game-changing solution. You've shared some incredible sources. And our mission today is really to unpack the evolution here.
See what's next.
Exactly. Reveal what's driving the next wave of innovation.
That's right. And it's a big wave. We're looking at a global magnetic sensor market projected to hit nearly, $4 billion by 2029?
$4 billion. Wow.
Yeah, and that growth isn't just random. It's fueled by this relentless demand for sensors that are smaller, use less power, and are way more precise.
Makes sense. More sensors everywhere.
Absolutely. So our goal here is to kind of illustrate how this relatively new technology, tunnel magnetoresistance, TMR for short, is leading this revolution.
TMR.
And really enabling the kind of smart devices we'll all be using tomorrow.
Okay, let's unpack that then. For years, Hall effect sensors they were everywhere, mainly because they were cheap.
Yeah, low cost was the main driver.
But they seem to be hitting a wall now, performance-wise.
Definitely. Especially when you look at accuracy, noise levels, and critically, power efficiency. They just consume too much for some modern uses.
Right. And then came AMR and GMR, anisotropic, and giant magnetoresistance.
Correct. They offered improvements, no doubt.
Right.
Better sensitivity than Hall, for instance.
But still not perfect.
Still face challenges, yeah. Things like complex packaging sometimes, sensitivity limits compared to what's needed now, and they often demanded higher current.
Okay, so what does this actually mean for, modern applications? Where's the gap that TMR is filling?
Well, think about demanding applications, like AR/VR, augmented and virtual reality.
Yeah, it needs precise tracking.
Exactly. Or really accurate indoor navigation on your phone, advanced wearables that monitor tiny signals. These are pushing the boundaries of what those older sensors can reliably do.
Okay.
And that's precisely why TMR has become so critical. TMR sensors, they achieve these incredibly high magnetoresistance ratios, the MR ratio, often soaring past 100%.
Whoa, hold on. Over 100%. What were the others, GMR and AMR?
Well, GMR typically hits maybe 8 to 10%.
Okay.
And AMR is down around 2 to 5%.
So a massive difference.
Huge difference. It's like going from a barely audible whisper to a crystal clear broadcast signal. And the physics behind it is where it gets really interesting.
How does it work then, basically?
TMR relies on this unique structure. You've got an insulating barrier, super thin, sandwiched between two magnetic layers.
Okay.
Electrons actually tunnel quantum mechanically through this barrier.
Yeah.
And the chance of them tunneling changes dramatically based on the alignment of the magnetic fields in those layers.
So the magnetic field controls the tunneling, which changes the resistance.
You got it.
Right.
And that leads to those superior MR values, that massive change in resistance.
So if you're listening and thinking about, the devices in your pocket or on your wrist, what are the core advantages? What makes TMR so transformative for your future tech?
Okay, several key things. First, TMR sensors offer ultra-high sensitivity. They can detect even the most minuscule magnetic field changes, things you just couldn't reliably see before.
So better accuracy, picking up weaker signals.
Exactly. Then there's ultra-low power consumption. Typically just 200 microamperes at 100 hertz sampling rate.
200 microamps, that's incredibly low.
It's a game changer for anything battery powered that needs to be always on. Think wearables, IoT sensors, every microamp matters there.
Absolutely. What else?
They also perform really reliably across a huge temperature range. In fact, sub-zero temps way up to 125.
Pretty robust then.
And significantly lower resistance, which is crucial if you're trying to detect really weak magnetic fields in biomagnetism. Things like magnetocardiography, ECG, measuring the heart's magnetic fields.
Interesting.
Plus, they offer true 360-degree sensing in a single device and enhanced robustness. Some have features like field shock recovery.
Field shock recovery, what's that?
It basically helps them maintain accuracy even if you get zapped by a strong temporary magnetic field, like from a speaker magnet nearby. They can also self-correct.
That's clever. Those are some really powerful advantages. Is cost or manufacturing complexity designers need to think about?
That's a fair question.
Yeah.
Initially, yeah, there could be higher upfront costs for TMR in some cases, especially compared to the basic. Fabrication is more sophisticated,
Right.
but the performance benefits often outweigh that.
Yeah.
Especially when you factor in the system cost savings, like needing smaller batteries or simpler integration because the sensor does more.
So overall system cost might actually go down?
Often, yes.
Yeah.
And the technology is maturing really fast, which is driving those costs down steadily. It's becoming much more accessible.
That makes a lot of sense. So, okay, connecting this to the bigger picture then, how are these cutting-edge TMR sensors actually being used, like in the real world right now?
Oh, they're enabling some significant advances.
Yeah.
In consumer electronics, you're seeing improved head tracking, 3D audio and AR/VR headsets, better hearables.
Okay.
Or that hyper-precise indoor navigation in smartphones we mentioned. In automotive, they're becoming vital. Think wheel speed sensors in EVs or highly accurate steering angle sensors for ADS, the Advanced Driver Assistance Systems.
Right, for safety and self-driving features.
Exactly. And for industrial uses, too. Highly accurate position and angle measurements in robotics, smart meters,
Yeah.
even precise current sensing for battery management systems in EVs or storage.
Can you give us like a concrete example, a specific sensor on the market that shows this off?
Absolutely. A really fantastic illustration is the Bosch SensorTech BMM350.
Okay.
Yeah. It's this tiny 16-bit 3-axis magnetometer. And when I say tiny, it's just 1.28 by 1.28 millimeters and only half a millimeter thick.
That's minuscule.
It is. And yet it consumes 94% less power than typical AMR sensors
94%.
and 80% less than standard Hall sensors. Plus, it's about 100 times more sensitive than either AMR or Hall.
Incredible numbers.
They really are. And what's truly insightful about this one is that patented field shock recovery feature we talked about.
The self-calibrating thing.
Exactly. It allows it to maintain its accuracy even when it's near magnets, like the ones you find on a smartphone loudspeaker, which used to be a real headache for sensor placement.
Yeah, I can imagine. So,
Thanks for watching. I hope you liked it or learned new things. Please also visit me on X, Instagram, or read my blog articles on WordPress. Bye.